For Module 5F, we're focusing on stoichiometric problems. So doing solution stoic. Stoic we learned in Chapter 4. Let's apply some solutions to it. Now, we're going to focus a lot on precipitation reactions. It doesn't mean that you have to have a precipitation reaction to do solution stoic. It's just the first time that we expose you to it in this chapter. So solution stoic as a whole is just using moles as your common ground, just like you do with regular stoic. Find the moles of your known solution, and then you convert to the unit of your unknown. Ask yourself, what am I trying to determine? How can I get there? I really like this graphic. I don't remember where I got it. If it's your book or the internet, doesn't matter. Biggest thing to note is that, as always, we're converting between moles and moles. Now, there's different ways to find moles. We can, if given the volume of a pure substance, we use density to get to mass of A, molar mass to get to moles. If given the volume of a solution, we use molarity to get to moles. Number of particles of A, Avogadro's number. So the main conversion factors you have here, density, molarity, and Avogadro's number. Density is if it's pure. Molarity if you have a solution. And then, of course, Avogadro's number if we're given number of particles, ions, etc. But we're still converting between moles because, again, we have to compare moles to moles here. That's like comparing apples to apples. And don't forget, molarity times volume gives you your moles. We do this calculation all the time. So, reaction synopsis. Here's some different types of reactions we're going to focus on this semester. There's more than these, but these are some good ones to kind of get you guys started. Precipitation reactions, which I call double replacement reactions. This is where you swap ionic partners. Some people have learned this in high school as the square dancing of the ionic partners, where they swap partners. I will show you guys what I mean by that when we get to that example. We have salt hydrolysis. This is where you have a basic species that steals a proton from water, and acidic species donate protons. We have neutralization reactions. This is a type of double replacement reaction. Weak bases accept a proton. Acids donate protons. So weak bases can accept protons. Strong and weak acids can donate protons. Weak bases don't accept protons. They form hydroxide, or strong bases form hydroxide in solution. So only weak bases are actually accepting those protons. We have redox reactions. Redox stands for reduction oxidation. We usually call these oxidation reduction reactions or redox reactions. You'll delve a lot more into redox reactions in second semester, but we do introduce them now. Double replacement, which produces a gas. There are three very specific situations where you will produce something, specifically H2SO3, H2CO3, or NH4OH, where these will further react to produce a gas. H2SO3 produces water and SO2. H2CO3, water and CO2, and NH4OH, water and NH3. So you see the pattern here. They're all producing water, but then the other thing they produce, SO2, CO2, and NH3, ammonia, these are all gases. We have metal oxides reacting with water and non-metallic oxides reacting with water. Combustion, you've already learned. Synthesis reactions and decomposition reactions. So again, there are additional categories that are useful as we try to predict possible products, but these are the first that we're going to really be responsible for this semester. The final authority, the final decision maker on what's happening is experimentation. We have, as scientists, we look at other people's work, we do work ourselves, and we do a series of experiments over and over and over until we can make a general trend, look at the patterns, and see what do we believe is happening. But bottom line, experiment always trumps theory. So as a scientist, as a chemist, I know that I'm trying to describe experimentation, but in the end of the day, the experiment is the truth and the theory is just a theory. I can fine-tune it, I can improve it, but I'm always just looking at a theory. So let's talk about some precipitation reactions. A precipitation reaction is a type of double displacement reaction where we swap ionic partners. For example, silver nitrate, soluble in solution, reacts with sodium chloride, also soluble in solution. to form silver chloride, which is insoluble or forms a solid, and sodium nitrate, which is soluble in solution. We call this a double displacement reaction because they've swapped ionic partners. The way this looks in solution, I've got a beaker with silver ions and nitrate ions. I've got a second beaker with sodium ions and chloride ions. I combine those two solutions into one big beaker. And when the silver and chloride ions find each other, they precipitate out, forming a solid. The sodium and nitrate ions continue floating around in solution because they are the spectators. So I have two soluble ionic compounds that react to form an insoluble product. The driving force of a precipitation reaction is the insolubility of the product formed. So the driving force of this reaction specifically is the formation of silver chloride. In order to do these, memorize your solubility rules, and then you use them to predict if an ionic compound is soluble or insoluble in water. Use it to predict if a precipitation reaction will occur. If you're forming an insoluble product, you are completing a precipitation reaction. So, double displacement reactions. Inspect your possible products that could be formed from the new combinations of ions and refer to your memorized solubility rules. Will an insoluble product, i.e. the precipitate, actually form? Here we're looking at Ki plus lead nitrate, so potassium iodide and lead 2 nitrate specifically. So potassium iodide and lead 2 nitrate. Now I see the balance reaction up here. I see precipitation forming. This is a common reaction that we'll do to show students what a precipitation reaction looks like. But let's see how we do it. We're going to swap ionic partners here. So I'm going to form KNO3, which I know is aqueous, and lead 2 iodide, which I know is, although iodide is usually soluble, lead 2 plus with iodide is an exception to the rule and is in fact insoluble. It will precipitate out of solution. I do need to balance my reaction. Now it's balanced. So in solution, I've got a solution of K plus. Now it's balanced. And I minus. I've got a solution of lead 2 plus and nitrate ions floating around. And when I mix them together, I've got the K plus ions still floating around, the I minus ions still floating around, the NO3 minus ions still floating around, and the lead 2 plus here. The moment this lead 2 plus and these two iodide molecules iodide ions find each other, this precipitates out. The K plus or potassium ion and nitrate ions continue floating around in solution because they are my spectators. So what do I do with this? Well, let's go ahead and first work through an example of just figuring out these equations. Write the equation for the precipitation reaction between an aqueous solution of potassium carbonate and an aqueous solution of nickel 2 chloride. Write the formulas of the reactants. Aqueous potassium carbonate. Potassium is K. Carbonate is potassium ion is K plus. Carbonate CO3 2 minus. That means I must have 2 potassiums for every 1 carbonate, and it tells me it's aqueous, which means it is soluble. Aqueous solution of nickel 2 chloride. Nickel 2 means nickel 2 plus. Chloride ion is Cl minus, which means this is reacting with NiCl2, and it does tell me it is aqueous. Determine the possible products. So crisscross. So if I crisscross, I'm going to get K and Cl coming together, and nickel 2 plus reacting with CO3 2 minus. You react that. So K plus and Cl minus coming together. So I crisscrossed and I crisscrossed. Write the formulas of your products, KCl and NiCO3. Determine if the products are soluble or not. KCl is soluble. Nickel carbonate is not soluble. That is insoluble, so we write it as solid. Don't let that S confuse you. S just means solid phase. And then write phase notation and balance your overall equation. So K2, CO3, aqueous, reacts with NiCl2, aqueous, to form KCl, aqueous, plus NiCO3, solid, and don't forget to balance. That is our overall balanced equation for what's described above. This is what it looks like. That's what nickel carbonate formation looks like. Nickel is green or blue depending on the pH of the solution, and that's what precipitates out. Okay, how about this? Lead 2 nitrate reacts with cesium sulfate in an aqueous precipitation reaction. What are the formulas of lead 2 nitrate and cesium sulfate? So first, formulas here. Write the molecular equation and net ionic equation for the reaction. What are the names of the products? So lead 2 nitrate, lead 2, Pb2 plus, nitrate, NO3 minus. Therefore, I know it's Pb, NO3 2. That is soluble. And cesium sulfate. Cesium, Cs plus, sulfate, SO4 2 minus. So CS2, SO4, that is also soluble because cesium is group 1. So I have written the formulas for this and this. Write the molecular equation and net ionic equation for this reaction. Well, let's complete the reaction. Swap ionic partners. So I'm going to form lead 2 sulfate, which is PbSO4, and cesium nitrate, which is CsNO3. Lead 2 sulfate is insoluble. Cesium nitrate is soluble. Don't forget to balance your equation. I need to put a 2 here to balance out my equation. This is my molecular equation. Let's see, net ionic equation. Net ionic is showing me exactly what's happening to form that precipitate. Net ionic ignores my spectators. In this case, cesium and nitrate are spectators because they're aqueous on both sides of the reaction. So PbSO4 is being formed from a sulfate ion and a lead 2 plus ion. This is my net ionic. Add names of products. This is lead 2 sulfate, and this is cesium nitrate. And that answers our question. Okay. What volume of a 0.1 molar magnesium chloride solution is required to precipitate all of the silver from 10 mils of 0.5 molar silver nitrate? Well, let's look at our equation. We want to know the volume magnesium chloride required for precipitating silver from silver nitrate. MgCl2 is aqueous. We're reacting that with silver nitrate. Also aqueous. Swap ionic partners here. We're going to form magnesium nitrate. which is aqueous, and silver chloride, which is insoluble. Now the question doesn't specifically tell me, but I am crashing out all of that silver as silver chloride. Balance my equation. I need 2 nitrates here to balance out my nitrates, 2 here to balance out my silver and my chloride. Then you don't have to, but I like to write under the equation what I'm given. So I know that I have 0.1 molar magnesium chloride, and I'm trying to find my volume. Unless otherwise specified, we probably mean milliliters. Put it this way, for my class, unless otherwise specified, we mean milliliters. I'm told that I have 0.5 molar silver nitrate, and I have 10 milliliters of it specifically. I'm trying to find the mils of magnesium chloride I need. So number of mils of magnesium chloride. I know I have a 0.5 molar solution of silver nitrate, which is 0.5 moles of silver nitrate to 1 liter of solution. And I have 10 milliliters of that solution, which is the same as 0.0100 liters of silver nitrate solution. That cancels out my liters of solution. Now I've got moles of silver nitrate. Now that I've got moles of silver nitrate, remember back to, sorry to scroll back so much for you guys, but remember back to here, what I've done right now is I've done this step. I've used my molarity to find my moles of A. Now I can go to moles of B. Then I can use molarity again to go to volumes of solution. So I know that I have 1 mole of magnesium chloride to every 2 moles of silver nitrate. That's for my balanced equation. That cancels out my moles of silver nitrate and gives me moles of magnesium chloride. I know I have a 0.1 molar solution of magnesium chloride, which means that if I had 1 liter of magnesium chloride, I would have 0.100 moles of magnesium chloride. So again, I can use molarity as a conversion factor. But this time, I need to flip the molarity so I can cancel out my moles and get my liters of solution. I do want this times 1,000 milliliters to 1 liter of solution, just to get my liters, or to get out of liters into milliliters. And when I calculate all this out, that cancels out liters, gets me milliliters. Calculate all of this out, and you should find the answer to be 25.0 mils of 0.100, I put too many zeros, 0.100 molar MgCl2. Couple things. Don't forget the decimal there, don't forget the 0. I need 3 sig figs. I can write it as 25.0. I could write 2.50 times 10 to the 1. I don't care, but don't forget the 0, okay? You need your sig figs there. What does this mean? What this means is if I had a 0.5 molar solution of silver nitrate and I had exactly 10 milliliters of it, if I was adding to that a solution of magnesium chloride that had a concentration of 0.1 molar, it would take me 25 milliliters to make all of that silver precipitate out as silver chloride. So what mass of calcium carbonate is formed if we mix 25 milliliters of a 0.12 molar calcium nitrate solution with 30 mils of a 0.1 molar potassium carbonate solution? Let's write a reaction. We're mixing calcium nitrate, so CaNO3, which is soluble, with potassium carbonate, K2CO3, which is also soluble. Swap ionic partners here. So I'm forming potassium nitrate, which is soluble, and calcium carbonate, which is insoluble. balance your reaction, and you're good to go. So I'm trying to find how much of this am I going to form. It's kind of nice when questions ask this because it kind of reminds you of solubility rules too. Because if I'm going to form the mass of something, then I'm clearly going to precipitate it out. Let's write down what we're starting with. We know that we have 120 molar calcium nitrate, and I have 25 milliliters of that, which is the same as 0.0250 liters. And I have a 0.110 molar solution of potassium carbonate, and I have 30 milliliters of that, which is 0.0300 liters. When you get volumes like this, where you have concentration and volume of both species, that means that yes, you do in fact have a limiting reactant question. So you can solve it a few different ways. I solve it a different way in the additional practice. I'm going to solve it one way in this example. So if you can solve it whichever way you like, I really don't care which way you want to solve it. But I'm going to solve it the more longer way, I guess, to say this example, just so you guys can see different ways to solve it. But the other way to solve it, which I think is actually the better practical way to solve it for students, is done in the additional practice if you want to see examples there. So let's say if calcium nitrate is our limiting reactant, then how many grams of calcium carbonate could form? I know I have 0.120 molar solution, which is 0.120 moles of calcium nitrate per 1 liter of solution. And I have 25 milliliters of that solution, or 0.0250 liters of that calcium nitrate solution. I multiply my volume by my molarity because that gives me moles of my calcium nitrate. Now that I have moles of calcium nitrate, I can easily convert to moles of calcium carbonate. It's 1 mole of calcium carbonate to 1 mole of calcium nitrate. Now I'm in moles of calcium carbonate, and now I can use the molar mass of calcium carbonate to determine how many grams I could form. Times 100.1 grams of calcium carbonate to 1 mole of calcium carbonate calculate this out, and you'll find it to be 0.300 grams of calcium carbonate. So this means if all of my calcium nitrate was reacted, I would produce 0.300 grams of calcium carbonate. But I'm not done. I have to figure out the other way too. What if potassium carbonate was my limiting reactant? How many grams of calcium carbonate could form then? I have 0.100 molar, which is 0.100 moles of K2CO3 to 1 liter of solution. I have 30 mils of that solution, so times 0.0300 liters of my K2CO3 solution. That cancels out my liters of solution. Now I'm in moles of K2CO3. So now I solve the problem just like I would any other time. Convert to moles of calcium carbonate. 1 mole of calcium carbonate is produced for every 1 mole of K2CO3 consumed or reacted. This brings me into moles, gets me out of moles of potassium carbonate, brings me to moles of calcium carbonate. So now I could go ahead and convert to grams of calcium carbonate. 100.1 grams of calcium carbonate per 1 mole of calcium carbonate. And when I calculate this through, I get an answer of 0.330 grams of calcium carbonate. What does this really mean though? What I have to do is I have to compare these two numbers. Basically the process that I followed this way is telling me that the first one, step 1 is telling me if I react all of my calcium nitrate, if nothing else limits my reaction, I just react all of my calcium nitrate, I will produce 0.3 grams of calcium carbonate. Number 2 is telling me if I react all of my potassium carbonate, nothing else limits the reaction, I just react all of my potassium carbonate, I will produce 0.33 grams of calcium carbonate. This is a smaller number. This is the most I can produce. What this means is that, calcium nitrate is my limiting reactant. Potassium carbonate is my excess reactant. That means that the calcium nitrate will run out, will all be reacted, but while there's still potassium carbonate in solution. It also means that the most I can make under these conditions is 0.300 grams of calcium carbonate. If I was to ask you how much excess was left, you'd be calculating how much excess of K2CO3 was left in solution.